Hello everyone, welcome to DP Tutorials by Donny Jarwa. In this teaching module, we will emphasize and accentuate on one important topic of discussion, which is the current loop behaving as a magnetic dipole. And also we will study one important property of a magnetic dipole, and that is its magnetic dipole moment. So we have learned from the preceding chapters that when you have a current carrying wire, always that current carrying wire will always have magnetic field, or the magnetic field will be associated with the wire. Say like for instance I have this coil which is carrying a current I. So this will be the direction of the current I. So we have the coil, and this coil is having a certain radius, and also it is carrying a current I. And likewise we know that there will be magnetic field lines produced by this current carrying coil or a current carrying loop. Now there are certain instances how to find the direction of the magnetic field on the basis of how the direction of flow of current is flowing on that coil. So we make use of this right hand rule, whereby if you take your right hand and then curl your fingers in the direction of the movement of current flow, which means that my curling the fingers is in this direction, which means that over here the current is in the anti-clockwise. This will be the direction of my current flow, which is in the direction of the anti-clockwise direction. So the direction in which this thumb is pointing, the direction in which that thumb is pointing, it is vertically upwards. So which means that this will be the direction of your magnetic field produced by that current carrying wire. So which means in this case the magnetic field which is produced by this current carrying loop is similar to the magnetic field which is produced by this bar magnet. Okay? A bar magnet is a type of a magnet which produces permanent magnetic fields. We already have been introduced that when we have a magnet, the magnetic field lines always emanates, or it always starts from the north pole and it goes to the south pole. Look at these arrowheads. The magnetic field lines moves from the north pole and it goes to the south pole. Even from here also it moves from the north pole and it goes towards the south pole. It moves from the north pole and it goes to the south pole. Whereas the field lines, this is field lines outside the magnetic field. So outside the magnet, so these magnetic field, okay, the magnetic field outside the magnet, that means there are two cases how to study the direction of the magnetic field. So if it is outside the magnet, the direction of the magnetic field line is always from north going to south. This is number one for studying the case of the direction of the magnetic field. Okay, for finding the direction of the magnetic field. Then number two, okay, if it is inside the magnet, that means when you look inside the magnet, since the magnetic field outside the magnet, it enters the south pole. So whereas inside the magnet, this magnetic field line, it moves from south to north. So the direction will be from south to north. So when you look from here, that means the field lines are moving in this direction. Okay, all the field lines are moving in the upward direction, which means that if I have a coil, and if the current in the coil is in the anti-clockwise direction, okay, governed by these arrow marks, which means that the magnetic field lines, there will be magnetic field lines, or magnetic field will be produced by this wire. So the magnetic field produced by these wires will be in this form. That means all they will start from in that direction. Okay, they will start on that direction. So which means that over here, these will be the direction of my magnetic field lines. Okay, this will be the direction of my magnetic field lines emanating from the lower direction going to the upward direction, which means you have been using this right hand rule in order to determine the direction of the flow of current. In that case also, this will be what? The direction of our movement of magnetic field lines. Okay, magnetic field lines. So from here also you will find out that means when you draw all these magnetic field lines, always it comes from the lower end and it is going to the upper end. When you look at this part, that means all across the upper part of the coil, okay, across we have two parts. We have the upper part of the coil, and from here this will be what? This will be the lower part of the coil. That means the magnetic field comes from the upper part, comes from the lower part of the coil and is going to the upper part of the coil. Which means if you compare this figure of the coil, this will be a current carrying coil. If you compare this figure of the coil with this of a bar magnet, that means the upper half of the coil will behave as a north pole because the direction are in the upward direction. So which means that this upper part of the coil will behave as what? The upper part of the coil will behave as the north. And this lower part of the coil, whereby the current enters, okay, starts from the north or is coming from the north, that means it is similar to the south pole of the bar magnet. So this south pole of the magnet will now behave as what? Will now act as the south pole. So which means that the upper portion of the coil will act as the north pole and the lower portion of the coil will behave as the south pole. All these red colored curves are nothing but magnetic field lines. These are nothing but one magnetic field lines. Okay, magnetic field lines. So these are the magnetic field lines. Then when you look with respect to these magnetic field lines, if you represent them in this direction, that means if you look with respect to this, that means this will be the direction of what? Of the magnetic field. That means if you try to complete this curve, that means with respect to this line, that means this will be the direction of our magnetic field. That means the direction of the magnetic field in this case will be what? Will be in the clockwise direction with respect to this end. If I divide this coil into two halves, and when you look with respect to this magnetic field line, okay, this magnetic field line, if I draw another closed curve, okay, if I draw another closed curve, since this is in this direction, so that will be taken on that direction, and then it will come across that part, and from here that means it will move. That means this arrow is analogous with this arrow. But when you look with respect to this aspect, in this case it is in the clockwise direction, but in this case the direction is in what? This direction. If you look with respect to your watch or your clock, it will be in the anti-clockwise direction. So which means that if I have a coil, okay, if I have a coil, suppose I take this coil, I draw the coil in that direction, and since the current is moving in this coil in the anti-clockwise direction, which means that there will be magnetic field lines. So these will be the direction of the magnetic field line. This will be the direction of the magnetic field line. Okay, this will be the direction of the magnetic field produced by that coil. This will be the direction of the magnetic field produced by that coil. So since when you look with respect to any coil, okay, when you look with respect to any coil, that means what do we have? Okay, when I will remove all those magnetic field lines, when you look with respect to any coil, that means there will be certain regions, okay, there will be certain regions, or there will be certain area enclosed by this coil. This will be what? This will be the area enclosed by the coil. Suppose let me write this as area A, okay, that will be the area A of the coil. Then from here, that means what is the concept of magnetic dipole moment? That means if I have a current I, when the current I is flowing across any conductor, that means if you multiply the magnitude of the current I with the area of the coil, that means that will give us the concept of magnetic dipole moment denoted by the vector M. So this is our definition of magnetic dipole moment. It is a vector quantity and is defined as the product of the current and the area. But of course, from here you might we might note down that both these current and area are themselves scalar quantities. But from here, in order to determine why does magnetic moment, okay, why does magnetic moment is a vector quantity, It is because of the reason that we have to indicate the direction of the area element vector. So which means from here, if this is the area of the coil, that means the direction of the area element vector is always perpendicular and upwards. That means this is the direction of our area element vector, represented by this unit vector n cam. Okay, represented by that unit vector n cam. See, like for instance over here, if I have a coil, say like for instance over here, if I have a coil on in this form, okay, the coil is in that direction, okay, the coil is in this form, and the current is moving in this direction. Okay, so that will be the direction of my current flow. So this region inside the coil, this will be what? This will be the area of the coil. So from here, that means what will be the concept of magnetic moment? So from here, the concept of magnetic moment is that it is a vector quantity, and from here that direction of the direction of the magnetic moment is always perpendicular and is governed by this unit vector, which is perpendicular to the magnetic field. So which means from here, that means the magnetic moment M, the magnetic moment M is equal to what? Is equal to the product of the current. This is the current I, which is moving. This is the direction of the current I, and also the area, okay, area of the coil, and also the direction of the area vector or area element vector. So from here, this is your what? This is your definition of magnetic moment. So since it is this magnetic moment, this is the definition of our magnetic dipole moment. This is the formula for the magnetic dipole moment. And this magnetic dipole moment, remember that it is a vector quantity. Okay, it is a vector quantity, and also since we are catering to different aspects of the unit of the magnetic moment, so we know that the SI unit of current is ampere, and the SI unit of area will be meter square. So the SI unit, this will be what? This will be the SI unit of the magnetic moment. Okay, this will be the SI unit of the magnetic moment. Now from here, when you look with respect to this coil, this will be one phenomenon where we have studied the magnetic field due to a current loop along the axis of the coil, which the description about, the explanation about the magnetic field generated by this current loop, I will give in the description, okay, below. Now just to reiterate what we have learned, that means from here, this is the direction, let this be the direction of the movement of current. Okay? Let that be the direction of the movement of current. So from here, let us rewrite, this will be the taken direction of the movement of current. So that will be the direction of the current flow. So we will look good in this aspect, that means the current is moving in the anti-clockwise direction. So your current over here, it is moving in the anti-clockwise direction, which means that if you, in order to find the direction of the magnetic field produced by this coil, that means it should be, you can use by this right hand thumb rule. So the right hand thumb rule, that means when you look with respect to this curl of the fingers, okay, when you look with respect to this curl of the fingers, the direction of the curl of fingers, that means this direction in which all the fingers are pointing, that means that will give us the direction of our movement of current. And this thumb, since it is pointing radially outwards, that thumb will indicate the direction of what? Of our magnetic field B. Okay, magnetic field B. So which means from here, the direction of the magnetic field is along the axis of the coil, which means that if I have this coil and if I place this coil along the different direction, this is the Z direction, this is the Y direction, and this is the X direction. And from here, that means this is the center O of the coil, and this is the radius R of the coil from O up to this spot, and this is the point along the axis. Let P be the point along the axis of the coil, OX. That means from here, when you look with respect to this aspect, this is the current which is moving in this direction. Make use of your right hand thumb rule. Then this thumb is pointing on that direction, which means that if I draw, okay, if I represent the direction of a field line, since this is the direction of my magnetic field B. Okay, since this is the direction of my magnetic field B. Okay, this is the direction of my magnetic field B. So which means that from here, that means when you look with respect to this aspect, the current, this is the coil, okay, this is the coil, and the magnetic field are moving on this direction. Okay, the magnetic field are moving on this direction, and the magnetic field also are moving on this direction. These are the direction of what? Of the magnetic field. Which means that this particular end, this end of the coil, where the magnetic field line appears to move out, that means this end of the coil, this end of the coil will behave as well. That end of the coil, let me represent by the white color, that means this end of the coil will behave as what? This end will behave as the north pole. Okay? This end will behave as a north pole. I'm talking about this end of the coil, that end of the coil. Whereas the other end of the coil, in which the current appears to go through, okay, this other half of the coil, that other half of the coil will behave as the south pole. Which means from here, that means since the current is moving on this direction, this other half which faces towards P, okay, this half of the coil which is facing towards P, that means this half of the coil will behave as the north pole, and the other half of the coil which is behind P or facing opposite to P, that will behave as the south pole. So which means in this case, that means the magnetic field lines will be, this will be the direction of what? Of our magnetic field line B. Also, we have discussed in the preceding section, that means these will be, if DL is direction of our current element, that means all this DL bar will be a what? Will be a element vector. Okay, element vector. And from here at this point P, that means since all these elements are at a distance r away from point P, and let this DL also be at a distance r away from point P. And with respect to the point P, from the center O of the coil, let x be the distance. Then from here, that means if you want to find the direction of dB with respect to point P, that means from the preceding section which I have discussed, which I will link in the description below, that means this will be the direction of the magnetic field along the direction of dl, which is perpendicular, okay, which means that this is perpendicular to this r bar. And even from here, the magnetic field of this element dl will be on this direction. So this will be the dB of what? Of this element. Now even this dB with respect to this element also, it is what? It is 90 degrees. So those are the certain things that you need to ponder upon. Let me repeat, the direction of dB is perpendicular to r bar, and even the direction of dB is perpendicular to r bar. That means this is 90 degrees. So those are the certain features. Okay? Those are the certain features pertaining to the aspects that this dB, okay, that dB should always be perpendicular to the radius vector. Then from here, that means from here also we have to note down that the angle between this observation distance, observation point, with the radius vector, with this PV, this R is your position vector. This R will behave as one, as the position vector. Even the R from here also will behave as a position vector. Since this is theta, then you can prove that this is also theta. You can also prove that this angle is also theta. Then with respect to this element, that means you have to resolve the respective components. So the respective components along the vertical direction, this will be this component along this direction, that means this will be, we have chosen last time, that means this will be dB cos theta. And with respect to this direction, this element also, this will be what? This will be dB cos of theta. We have shown over here. And with respect to this element also, we have another element which acts on this direction, okay, which acts on this direction. So that element which is given by this pink colored vector, this will be what? This will be dB sine of theta. Even for this lower element, for the upper element, we have this component of dB along the vertical direction, which is pointing along the x-axis, dB sine theta. And with respect to this dl, this element from the lower end of the coil, that means the direction of vertical component, the vertical component of this DL also will act on this direction. That means they are in the same direction. So which means that we have all these dB sine, see this component of dB, that means dB sine theta are acting on the same direction. So that is why when we have also discussed last time that the magnetic field due to this current carrying circular loop which is at a finite distance along the x-axis is given by certain expression, and this expression is given by B equals sine mu naught I r square divided by 1 divided by 2 x square plus r square, and then to the power 3 by 2. So this is that expression which we have deduced previously, where this I is the current on this loop, and this R is the radius of the loop, that capital R is the radius of the loop, and from here this x which we have mentioned over here, that x is the observation, the distance of the observation point along the axis. So from here that x is the observation point, the distance of the observation point from the axis along the axis of the loop. Then from here we have also discussed that the direction, how to find the direction of B. You can find the direction of B by using the right hand thumb rule. So from here we will have to study, we have to emphasize upon this relation in order to illustrate the magnetic field of the coil resembling the magnetic field of the bar magnet. Our strategy over here is that I want to show that the magnetic field, this is the coil, that means the magnetic field of this loop should be the same as the magnetic field of what? Of the bar magnet. That means both should have the same formula. That means magnetic field, the magnetic field generated by the coil, the magnetic field due to the coil, the magnetic field due to the current carrying coil should be the same as the magnetic field produced by that bar magnet, That is my target. That is my target. That means I want to show that the magnetic field of the bar magnet will be the same as the magnetic field produced by the current carrying coil, so that we can explain all these certain features and certain realities that the magnetic field are being generated by this coil. So these are something, this is the main formula, step number 1. Step number 1, that means you have to know this equation. I'll mark that as equation number 1. Then equation 2, that means in order to reduce the magnetic field of the coil, that means from here we will put certain assumptions, and that assumption is that when this distance x is very large comparison to r, which means that when x is very large in comparison to r, that means your observation distance is very large. When I say very large, that means we write by that greater than sign, x very large in comparison to r. Then when this x square is very large in comparison to r, which means that r square term can be neglected. Let us emphasize from the diagram. From the diagram itself, it is very evident. It is very evident that this r, or this x distance, that means this distance OP, is very large than this distance r, or that x distance is very large in comparison to r. From the figure also, it is very obvious that this is larger than r. So if you square the smaller value, that means it will be even smaller. It will be even smaller. So r square term can be neglected under that condition. So from here we can write certain assumptions. That means from here, that means when r square term can be neglected, we will look with respect to this denominator term of equation 1. The denominator term of equation 1, that means we have this expression x square plus r square. That means this, when we neglect r square, that means this expression is approximately equal simply to x square, which means that equation 1 take this form now. Okay, take this form now. That means from here you have this expression of mu naught I r square divided by 2. That means since this bracket term is replaced by x square, so we will write only x square. But over here we have the power 3 by 2, so you will write 3 by 2. Which of course when you solve this expression, that means you'll get mu naught I r square divided by 1? Divided by 2 to the power cube. Since this 2 and 2 will get cancelled. Now from here, another important logical step that we need to do is that let us multiply and divide. Okay, on this equation, let us multiply firstly, and then secondly we will divide, multiplying and dividing this equation, the above equation, by twice pi. So when you multiply and divide by twice pi on this particular equation, that means we got certain conditions. So over here I have mu, so I will take mu naught, and we have the 2 value, so I will put this 2 over here. Then what did I write over here? We will multiply and divide. Let us first divide by twice pi, and then over here we will multiply by twice pi. So which means that I will multiply by twice pi and at the same time divide by twice pi. Over here we have what? We have those terms, which is what? Which is I r square, and over here we have that x cube term. Now from here we have to do certain rearrangement. That means from here we have mu naught, and if you multiply that, that will be equal to mu naught by 4 pi, and from here we have that 2, and then we will do some grouping. We will put I first here, and then we have pi and r square, then we will group that pi and r square together. We will group that pi and r square together. So this will be pi r square. So it means the same. But from here, when you look with respect to that coil, the coil is in this form, and the current I is moving from here, and this is what? This is the area of the coil, or in other words, if you multiply the area of the coil will be what? Since you have the radius, this will be what? This will be the radius. That means from that point up to that point O, that means what is that? That is your radius, which means that this area in between the coil, this will be what? That means the area of the coil will be equal to what? Pi r square. So this, what is this pi r square? That pi r square will be the area of the loop, or of the current loop. Okay? The area of the current loop. So I will write here area of the current loop. Area of the current loop. So which means from here vectorially, that means from here, even if you want to represent the direction of that n cap, okay, that magnetic moment will come from that instance from there. So which means that from here we have this expression. That means we can write in this form. That means this will be mu naught divided by 4 pi, and over here you have twice I, and what is this bracket? All this term inside the bracket, that is nothing but the area of the loop, of the current loop, divided by 1, divided by x cube. And from here, what is this concept of IA? This concept of IA is what is known as the magnetic moment. Magnetic moment is M equal I into A. So the magnetic moment, this we can replace, we can again rewrite that in a simpler form. That means mu naught, not twice pi, mu naught by 4 pi, okay, twice capital M divided by 1, divided by x cube. So this will be the final form, for the expression of the magnetic field, okay, the magnetic field due to a current loop. And this expression is similar, okay, this expression is similar to the expression of the bar magnet to the expression of the magnetic field generated by the magnet. Since magnetic field is vector quantity, so that is why I put by this vector notation B bar. And even this M bar also is a vector quantity. This is a vector quantity. Okay? So in magnitude, okay, of course in magnitude that means m will be equal to ia, but keep in mind that this mia is a vector quantity. So which means in vectorially, this magnetic moment can be written in this form: m equal ia with the n cap, which is the direction of the area element. So this will be what? This will be your magnetic moment. Okay, this is your magnetic moment. So from here, the above equation, let me mark this as equation 2. Okay, let me mark this as equation 2. The above equation 2 gives the magnetic field due to the current loop, which is similar to the magnetic field of the bar magnet. So you have to arrive till this condition, okay, till that condition. So from here we can see from the current loop it has the following properties. Number 1, it produces magnetic field. Okay, it produces the magnetic field. It produces the magnetic field. It produces the magnetic field, and it behaves like a magnetic dipole at large distances. Now, the current loop is the only elementary current that causes what? That causes the magnetic field. And point number 3 is star mark, okay, whereby the magnetic poles north and south of the magnet produces magnetic field lines which are similar to the field lines produced by the current loop. Let us just emphasize and reiterate some of this discussion which we have learned. So this is your bar magnet, and this is the north pole of the magnet, and this is the south pole of the magnet. So the magnetic field lines always will move on this direction. The magnetic field lines will always move on that direction. That means from the north going to the south. Okay? From the north going to the south. That means from here, if I keep on finishing this, from the north it goes to the south. So these are the direction of the magnetic field line. If I have a coil of that form, and if the coil, if I have a coil of that form, this will be that coil, okay, and the current is moving on this direction, okay, the current is moving on this direction, then there will be magnetic field associated, or magnetic field will be produced by the coil, okay, will be produced by the coil. So this will be the direction of my magnetic field, which means that this upper portion of the coil will behave as what? That upper portion of the coil will behave as the north pole, okay, whereby the current is, the direction of the magnetic field is in the vertical upward direction, and from here on the lower part of the coil, the current is moving in the magnetic field, it is moving on this direction. So the lower part of the coil will behave as the south pole. So when you compare between this coil and this magnet, when you compare between this coil and this magnet, the magnetic field lines generated by this current carrying coil and the magnetic field line created by this bar magnet are analogous, or are the same. So you just go through the entire lecture so that you will have a clear understanding, and your concepts will be clarified. Until we meet again, thank you.